Okay, so good afternoon and welcome to the oral defense of the thesis of Darvy Ong. The title of his thesis is Student Risk Assessment, Identifying Contributing Factors and Predicting Success in Graduation of Undergraduate Students in the College of Engineering. So the panel members include Dr. Joanna Rodet Pedraza, her advisor, Dr. Anastasia B. Alvarez, panel member, and me, Dr. Franz De Leon, as the panel chair and reader. I'd also like to welcome our viewers through Facebook. So Darvy, you may start your presentation now.
Okay, so good afternoon, everyone. I'm Darvy Ong, and today I'll be presenting my thesis on student risk assessment, identifying contributing factors and predicting success in graduation of undergraduate students in the College of Engineering. So, the University of the Philippines, known as our country's premier state university, upholds a high standard when it comes to the quality of education that it provides. We are expected to hold in the highest regard the qualifications a student must meet in order to enter and graduate from our institution. As such, this study aims to provide an insight on how different factors may affect a student's chances of graduation in the university. We will be looking at the Diliman campus, particularly in the College of Engineering. It is a known fact that the College of Engineering is the largest college inside the campus, with with 8 departments or institutes, 12 undergraduate programs, and over 5,000 students. As members of the College of Engineering, we are interested in learning how students from different socioeconomic backgrounds fare in our college. Now, before moving on to more technical details, let's define some terms that will be used extensively in this presentation. First, freshman is defined as a student who has passed the UCAT and chose to take up an engineering degree program inside the college. We will not be including shifties, transferees, second-degree students, as these students enter the college through different means and as such are subject to a different line of analysis. Next, we have the maximum residency rule, or the MRR, which is a rule that sets a limit on the number of years a student may enroll in the College of Engineering without graduating. Typically, the MRR is computed as 1.5 times the degree program curriculum's prescribed number of years. This table shows us the different degree programs inside the College of Engineering, as well as their curriculum duration and calculated MRR. After that, we also have student success, which is defined as the successful completion of a student's goal in degree attainment. In particular, a student who persists and graduates in their chosen degree program. In this study, student success is defined as persistence until graduation and can be divided into 3 categories. First, graduation in their degree program. Second, graduation in their original department. And last, graduation in the College of Engineering. In this study, only full-time freshman students who have graduated within the MRR will be considered. All other types of students, such as those who exceeded the MRR, are considered as outliers and will not be included in this study. Finally, persistence until graduation is the statistic comparing the count of any set of students between their initial enrollment and any subsequent enrollment. This accounts for students who enroll under the College of Engineering and remain in their original degree program or department or college until graduation, and is computed as follows. It is the sum of the freshmen from a particular year who graduated over the sum of all freshmen from that particular year, with the numerator possibly changing depending on the context of the analysis. Next, using this equation, we were able to identify the freshman graduation rates for the following. Presented here is a number of freshmen that the college accepted from batch 2009 to 2013, as well as the total number of students over the said years. This first statistic shows us the percentage of students who graduated in the College of Engineering, regardless of which degree program they enrolled in and graduated in. We see from this that the percentage of students who have graduated in the college have decreased over the years, with an overall graduation rate of 66.69%. Furthermore, looking at those who graduated in their original degree program, we can see that there is a large decrease in graduation rates with around 6 to 12% decrease between the graduates in engineering and graduates in their original degree program. Finally, we look at those who not only graduated in their original degree program but also on time as well. We see that generally the conversion rate from freshman to graduate in the college is not promising since it decreases increasingly. So these numbers reflect the widespread belief about the college that while it is hard to enter the college, it is even harder to graduate from the college, if at all. Furthermore, if we are to compare our overall college graduation rate of 66.69% to those from other well-known engineering schools abroad, such as UC Berkeley and MIT, we can see that there is a large disparity between our graduation rates. This gives rise to the question, what factors are affecting the graduation rates of engineering freshmen inside our college? And given a student's educational and socioeconomic background, what is the probability that a freshman student will persist until graduation? These are the questions that this study aims to answer. Moving on, we will now discuss different works which touch on student success. Studies on student success can be classified into two categories, those that use descriptive statistics and those that use predictive analysis. Under descriptive statistics, we see studies that focus on studying year-on-year persistence and graduation rates, and studies which use factor analysis and identification to determine student characteristics that affect student success. On the other hand, with predictive analysis, studies tend to focus on predicting student persistence or graduation through the use of different machine learning models. Some of these studies using statistical analysis are as follows. First, Isopportally use exploratory factor analysis to find the relationship between engineering student performance in their first year and different factors such as SAT score, interest in science, and gender. They found that out of the factors, SAT math scores and taking extra classes in math and physics were significant to student performance. Furthermore, Taylor and Orr used logistic regression with backwards elimination to identify factors that affect graduation in students. They found that high school GPA, ACT Science, ACT Math, and ACT English affected graduation. Next, Scalise, Westerfield, Saker et al. Also used logistic regression to create models using goodness of fit test and odds ratio, and they found that SAT score, high school ranking, gender, and participating in summer bridge programs have an effect on probation probability. And finally, Zhang, Anderson et al. Used multiple logistic regression to create models for graduation using wild chi-squared statistics to determine significant factors. They found that high school GPA, gender, ethnicity, SAT quantitative score, and SAT verbal score and citizenship have had an effect on student graduation. We see from these studies that the most prevalent statistical method is using logistic regression to identify important factors. It should be noted, however, that while these studies found significant factors, the amount of variance explained by these methods are not that high, which is why we will also be looking at predictive models for classification. Studies focusing on predictive models are as follows. First, Karamuzis, Viretos use artificial neural networks to predict student graduation using 9 different factors. And out of this, they found that present age and disability status had a significant effect on student graduation, and they also achieved an accuracy of 68%. Furthermore, Alcazone, Hobson used neural networks to predict student retention with 6 factors, and they achieved an accuracy of 70.1%. Next, Pang Jug et al. Used support vector machines or SVMs to predict student graduation with over 100 factors. These factors are a mix of both qualitative and quantitative factors, and depending on the mixture of factors they use, they found that the model accuracy ranged between 60% to 85%. And finally, Gopalakrishnan, Kasset et al. Used a variety of different machine learning techniques to predict student retention and graduation using 12 pre-college factors, and they found that the naive Bayesian model is the best one for predicting graduation, while the Adibus or SVM is the best for predicting retention. These methods, while useful for creating high accuracy models in predicting graduation rates of students, make it more difficult to identify important factors affecting student success, since all known data is used without discrimination to predict the student success chances. As summary, this study will utilize these techniques, which will be discussed in further detail in the methodology. Now, for the problem statement of this study, existing work on analyzing student persistence until graduation focus on using machine learning algorithms on all student information in a dataset to get a probability score, while other studies use descriptive statistical models to identify student factors that have a significant effect on persistence and graduation. These approaches, while effective in helping identify the major contributors to the outcome and determining the probabilistic effect of certain student factors, have never been used in the setting of the College of Engineering and the University of the Philippines Diliman, thus making it difficult for us to draw meaningful conclusions specific to the students of our college and university. In order to answer this problem, our study aims to identify student characteristics from pre-matriculation and during college life information that may affect the persistence until graduation of students in our college. More specifically, we will perform descriptive analysis on available student data, formulate a method or process for identifying risk factors and predicting student graduation, and use available student records to create statistical and machine learning models for predicting student success. To further contextualize this study, the scope of the study was limited as follows. For the data, only student data from freshmen between batches 2009 and 2013 are used in the study, which include the following. For the analysis, it should be noted that all collected data are from students who did not undergo the K-12 program. As such, analysis results should not be imposed on students post K-12 implementation. And that while we originally planned to perform further analysis on year-on-year persistence of students, the Data Privacy Act limited the amount of information we could collect regarding students from the said period, which is why we opted to focus on studying information provided by the college and the Office of Admissions. Now, let's talk about the methodology of this study. This flowchart presents an overview of how the study was conducted. First, we gathered data from different sources, which we then use together with different data transformation techniques in order to be used with our data analysis and data modeling blocks, wherein we use descriptive statistics and factor analysis, as well as different machine learning methods to identify significant factors and to model student success predictors. Each of these parts will be further expounded in the following sections. Furthermore, we use Streamlit and Docker in order to create a simple web application which is capable of accessing and modifying data, modeling datasets, visualizing results, and generating report files from these results. These are packaged in the following modules and are used to process and generate results using the collected student data. Now, to gather the required information for this study, we acquired data from the following sources. First, the Office of Admissions. From the Office of Admissions, we requested pre-matriculation data, including UPCAT scores and other UPCAT registration-related information. From the College of Engineering College Secretary Office, we acquired official list of freshmen, transferees, shiftees, second-degree takers, and graduate students, which we then cross-validated with data from the College of Engineering archives. From the UP Computerized Registration System, or UPCRS, we were able to generate some standard reports on student data which were made readily available. These data were then merged into one big database and were subject to further preparation and processing. After processing the data and removing factors outside the scope of this study, we had a total of 27 different factors, 26 of which were input factors and 1 output factor, which is graduation status. The final dataset columns are as follows. We see from here that almost 2/3 of the columns are categorical factors, while the remaining are continuous factors. It should also be noted that the output factor is a categorical factor, also with 2 values, yes or no, depending on the student's graduation status. Finally, out of the 26 input factors, only these 4 are post-matriculation factors. The rest are pre-matriculation factors. Next, after identifying the factors to be used for analysis, we create data subsets in the dataset. All in all, 7 datasets were created. First, the main dataset, or the all-freshman dataset. This dataset provides us with an overview of all the degree programs in the college. Next, the main dataset was further divided into 2 datasets based on the number of years in the degree program's curriculum. This resulted in the BSCS dataset and the non-BSCS dataset. Furthermore, we also created a subset for the AAAI since we are interested in seeing how the AAAI performs against the college. And finally, we created datasets for each of the 3 degree programs inside the EEE as well for a more specific analysis on each of these degree programs. The 7 datasets have the following characteristics. Originally, we had a total of 4,821 data points in our database, but after validating our data, we found that 6 of these were either non-major students, second-degree students, or transferee students. This resulted in the final 4,815 data points for the entire dataset. The breakdown for each of the datasets are as follows, with details on further data point removal due to dataset scope or the data point having missing values enumerated below in this table. The final number of data points can be seen in this last column, where we see that for all datasets, except for the BSEE dataset, we have more than 550 data points, which provides us with enough data to analyze and make general statements on these datasets. Before proceeding with the analysis, there was a need for us to convert the categorical factors into numerical format for use with the statistical and machine learning techniques. To do so, we utilized one-hot encoding, which converts an n category factor into n-1 category numerical columns. This process is illustrated as follows. For example, we have a factor sex, which has 2 categories, male or female. If we are to convert this using one-hot encoding, we will get 2 different columns, one for male and one for female, wherein the rows that were original male has a 1 in the male column and 0 otherwise, and the rows that were female originally has a 1 in the female column and 0 otherwise. Afterwards, since we created n different columns here, we look at the number of occurrences of 1s in each of these columns, and we remove the column with the least number of occurrences of the 1. So this is done in order for us to avoid multicollinearity in our final dataset. Next, we use Pearson's correlation coefficient to identify continuous factors related to each other. Pearson's correlation is computed between pairs of factors x and y using the following equation. This results in a value between -1 and 1, where a value closer to 0 means there is a negligible correlation, while a value closer to +1 or -1 means there is either a negative or positive correlation between the factors. For this study, we will be using a cutoff value of 0.5, wherein all Pearson's correlation values greater than or equal to 0.5 are considered as highly correlated to each other. As an example, the correlation matrix above shows us that the UPCAT average t-score and the UP predictive grades has correlation values higher than 0.5, and as such, they will be removed before analysis. Next, for categorical factors, we use a similar approach, but instead of using Pearson's correlation, we use Kramer's V to check for associations between categorical factors. This equation yields a value between 0 and 1 with values close to 0, meaning minimal association between factors, and values closer to 1, meaning higher association between factors. Similar to Pearson's, the cutoff for Kramer's V is also set to 0.5 with values higher or equal to 0.5 considered as highly associated factors. As an example, this table here shows us that the school type, which is this one here, has a high correlation with high school province with the value of Kramer's V value of 0.53. In cases such as this, we choose to remove the factor with more categories since doing so will lessen the amount of variance in our dataset. So in this case, school type is removed. After doing this, we then proceed with data analysis. First, we perform descriptive analysis on the dataset, particularly the all and the EEI datasets. Simple statistics on graduation rates of students in the college for the past 5 years are generated and are listed as follows. Furthermore, we will also be creating simple statistics comparing the different each of the factors with the graduation status. Doing so will provide us with an idea on how each factor is related to the graduation status and how the EEI and the college compare with each other in terms of graduation statistics. Afterwards, we will proceed with statistical analysis, in particular, the use of logistic regression to model the effects of the factors as a whole on the graduation status. We use logistic regression to do this since our output factor, graduation status, only has 2 categories, and by using this equation, we can create a sigmoid curve by optimizing the coefficients of each of the factors using maximum likelihood estimation, or MLE. Finally, it should also be noted that this can also be used to predict graduation status. After creating the logistic regression model, we use the likelihood ratio test to determine whether or not the model is significant. Computed as follows, the log likelihood ratio is used with the chi-square distribution to determine the p-value of the model, where p-values less than 0.05 indicates strong evidence against the global hypothesis, meaning the independent variables collectively predict graduation and retention at the 0.05 significance level. Additionally, we also use McFadden's pseudo R-squared to compare between models using the same dataset. It should be noted that models with McFadden R-squared values between 0.2 and 0.4 are considered as good fit models already, contrary to the usual R-squared statistic. Furthermore, using the logistic regression model, we determine factor significance using the wild chi-squared statistic computed as follows. This is then used together with the chi-squared distribution to produce a p-value, where a p-value less than 0.05 indicates that the input factor being tested is significant at a 95% confidence level. Additionally, after identifying significant factors, we can measure the effect of each of the significant factors using odds ratio, which is computed by raising the coefficient of each of the factors to e. For continuous factors, this can be interpreted as an increase in odds per unit increase in the odds ratio. For categorical factors, on the other hand, this is the ratio of odds between levels or categories in a particular factor and may be interpreted as follows. For odds ratios equal to 1, it means that there is no difference in effect between the 2 categories. For odds ratios less than 1, it means the first category has a lower odds of graduation as compared to the second. And for odds ratios greater than 1, it means the first category has a higher odds of graduation compared to the second. Finally, to ensure the validity of our odds ratios, we use a 95% confidence interval, where a large interval means more uncertainty in our analysis, and smaller intervals mean that we are more certain of our results. Finally, after identifying factor significance, we proceed with creating prediction models for our datasets. But before that, we split the datasets into training and test data with a 70-30 split between training and test data. The training data is then used in conjunction with different machine learning models, and to ensure the robustness of the model, we further divide the training data into 5 folds, requiring us to train the model a minimum of at least 5 times and to identify the best model based on the optimization parameter, which in our case is the AUC ROC, which will be discussed shortly. In this study, we will be focusing on 3 different machine learning models. The first being logistic regression, which we've already discussed, and the other 2 being support vector machine and neural networks. Support vector machine classifies data using a hyperplane that separates data points. The hyperplane is found by maximizing the margins from the support vectors. In this study, we will be tuning the following parameters in order to get the best fit model, and we use class weights set to balance in order to prevent our model from being bias towards a particular category in a factor. And we use grid search to find the best parameters for the model. The neural network, on the other hand, creates a nonlinear classifier using multi-layer perceptron or MLPs with hidden layers. In our case, we will be using an MLP or a neural network with only one hidden layer, and the following parameters will be optimized as well using grid search. Finally, in order to evaluate the performance of the predictive models, we use different performance metrics to compare the models with each other. First, using the models, we create the confusion matrix by comparing the predicted outcomes with the actual outcomes. This provides us with an insight on the following. First, the true positives, which is the number of positives that we predicted that were actually positive. Next, the true negative, which is the number of negatives we predicted that were actually negative. Then we have the false positive, which is the number of positives we predicted that were actually negative. And finally, the false negatives, which is the number of negatives we predicted that were actually positive. It should be noted that in this study, a threshold of 0.5 is used to differentiate between a yes and no in the output factor. Using these, we are then able to compute the following metrics. First, we have recall or the true positive rate, which tells us about how much we predicted correctly out of all the positive classes. Then we also have precision, which tells us how many are actually positive out of all the positive classes that we predicted. Then we have accuracy, which tells us about how much we predicted correctly out of all the classes. And finally, the false positive rate, which tells us about how many false positives we had in our prediction. And aside from this, we also have another metric called the F measure, which utilizes the recall and precision to give us a score on the model. This is useful in making comparisons between different models. Furthermore, to give us more insight on the performance of the model, we generate a receiver operating characteristic curve or ROC curve, which is a probability curve that measures model performance at various threshold settings. This tells us how good the model will be at differentiating between yes and no at different threshold settings with the AUC score as the measuring metric. AUC values near 1 indicates good separability between the output classes, and values closer to 0 means the model has bad class separability. Now, we will discuss the results of this study. First, using the Pearson's correlation, we identified that the following factors have high correlation with the other continuous factors, which is expected since these were computed using the other UCAT factors. And thus, these factors were removed from the dataset. All other datasets showed similar correlation matrix values, therefore the same 3 factors are also removed. Next, we used Kramer's V to identify associations between categorical factors. For the all non-CS, EEE, and BSECE datasets, we found that high school province and school type are highly associated with a Kramer's V value of 0.53. In this case, school type is removed since it has more categories. On the other hand, for the BSEE dataset, we found that had a scholarship has a high association with year of first enrollment. The year of first enrollment is removed since it has more categories, and we want to retain had a scholarship, which is a post-matriculation factor. Finally, for the BS-COE and the BSCS datasets, no factors were found to have high association with each other. After removing the correlated and associated factors, the final number of factors and rows for each dataset are shown on this table. It can be seen here that additional factors have been removed from each of these datasets due to lack of data variance in these factors. For example, the civil status factor only had one category, which is single, for all of the data points, and thus had to be removed. Another example is the country of citizenship, which only had 2 categories, either Filipino or foreign, with less than 10 data points in the foreign category, which resulted in minimal variance in that particular factor, so it was removed as well. Similar procedures were done with the rest of the factors listed here. So we can see from this table as well that for each data set, two different models were made, Model 1 and Model 2. Model 1 is the model using only pre-matriculation factors, and Model 2 is the model that includes all factors that we have. This was done so that we may compare the results of using only pre-matriculation factors for graduation prediction with the results of including post-matriculation factors or in-college factors in graduation prediction. This next section will discuss the graduation rates of the college and the EEI. First, we look at the college-wide graduation rates of the College of Engineering. We see that overall, we have a 66.69% freshman graduation rate in the College of Engineering. And it should be noted that the overall percentage of graduates is going down for BSCS, while for non-BSCS, it is pretty constant. Next, for degree program graduation rates in the College of Engineering, we have an overall of 58.06%, which is less than the college-wide graduation rates. In this chart, we see that the performance is actually pretty similar. For the entire college, the graduation rate is pretty stable, and for non-BSCS, it is stable as well. And for BSCS, it is also decreasing. And finally, for on-time graduation rates, we have an overall 39.53 graduation rate, where we see that the BSCS has decreased significantly over the years, while the college retained much of the same graduation rate over the years. Next, looking at the EEI statistics, we can see from this plot that overall, the college-wide graduation rates in EEI is 56.79%. And we see that there's an increasing trend in all of the in EEI overall, and in each of the degree programs in EEI, with the exception of year 2013, which may be due to the lack of data for delayed students who are in their 7th year or more. Next, we also see that institute graduation rates have increased in general, except for BSEE, with an overall institute graduation rate of 47.13%. And next, we also see that here, the degree program graduation rates for EEI has an overall value of 41.70%, wherein the graduation rates for EEE in general is increasing, for BSECE and for BSCOE is increasing as well, while the BSEE has a decreasing trend. Finally, the overall on-time graduation rate for EEE is 25.49%, which is lower by 14% compared to the college level. And we see here that while the overall graduation rate of EEE is still constant, the BSCOE is increasing, the BSECE is also increasing, and again, the BSEE has a decreasing trend. Next, after looking at the graduation rates, we now look at the number of semesters it takes for students to graduate in the college and the EEI. First, we look at the overall performance of non-CS and BSCS students. We see from here that for BSCS students, overall 65.65% graduated on time, while 96.68% graduated within the MRR. On the other hand, for non-BSCS students, 65.21% graduated on time, and 97.61% graduated within MRR. Looking further at each of these, we look at the yearly distribution for BSCS. So we see here that the trend pretty much stays the same, with a large variation here on the on-time rates for BSCS, varying between 50 and 80% in graduation rates. But for those who graduated within MRR, it typically rises to 90% before the MRR. On the other hand, for non-BSCS, the trend stays the same, or trend is pretty similar for all 5 years, with graduation rates around 60 to 70% and above 90% graduating before the MRR. Next, looking at the EEI distributions as well. First, we look at this one. So the red line here, this is the college 5-year degree programs rate of graduation or the number of semesters. The yellow line, which is covered by the purple line here, is the overall EEI number of semesters to graduation line is lower than the college level. And for each of the degree programs, it is lower as well. Overall, we can see that 56.97% of EEI students graduate on time, while 96.55% graduate within the MRR. Breaking this down further into yearly rates, we see that the trend for EEI is pretty much the same over the 5 years, with graduation on-time graduation rates ranging between 50 to 70%, and MRR rates rising above 90%. This next plots show the breakdowns for each of the degree programs within the EEI. But basically, what we can say here is that for all degree programs within the EEI, the on-time graduation rates for all 5 years are pretty constant, with an overall graduation rate above at least 50% for each of the degree programs, and graduation rates above 95% for the MRR. Next, for this section, we will be looking at the distribution of each input factor as compared to the graduation status. This will provide insight on how each factor is related to the graduation rate. First, we have degree program upon entry. Looking at these plots, we can see that for the college level, the BSIE, BSME, BSCE has the highest graduation rates, while BSCS, BSE, BSCOE, and BSECE have the lowest graduation rates. The graduation rates across the years are relatively constant for all degree programs. Next, we have religion. And looking at these plots, we can see that Christians have the highest graduation rates, regardless of the type of Christians, may they be Catholic, born again, or even evangelical Christians. While atheists, agnostic, and those with no indicated religion have the lowest graduation rates. It can also be said from these plots that there is no clear attribute between the religion and graduation status across the years. Next, we have entry STFAP or STS bracket. Looking at this plot, it can be said that students from higher income brackets have a more constant rate of graduation as compared to those coming from lower income brackets. Even though the students coming from brackets E1 and E2 have the highest graduation rates in both the college and EEI level, we can't be certain about this because we only have a few data points for this type of students. Next, for school type, looking at these plots, we see that students who come from state universities, private, or science high schools have higher graduation rates as compared to those coming from public high schools or foreign high schools. Furthermore, for address location, we see that generally students with permanent addresses nearer to the address location of the university campus have a higher graduation rate as compared to those coming from farther away, such as, let's say, Visayas or Mindanao. Next, for high school province, we see that those who studied in Luzon have increased rates of graduation compared to those from Visayas or Mindanao. And furthermore, looking at dependence on UP faculty or employee, we see that generally dependents on UP faculty or employees have a higher graduation rate as compared to non-dependents, but not by much. Again, it should be noted here that we only have a few data points for dependents, so this is not a very clear-cut comparison. And next to that is students who are members of minority groups or members of ethnic groups. So from this plot, we again see that students who are part of minority groups have a lower graduation rates as compared to those who are not from minority groups. Next, for sex, we see from these plots that generally sex doesn't affect graduation chances within the college and the triple EI. Next, for those who enrolled in their first or second choice degree programs, we see that enrolling in their preferred degree program has a very positive effect on graduation, with graduation rates increasing around 20% between those who enrolled in their preferred programs and those who didn't. And finally, this is not the last one. So for shifted within engineering, we see that those who shifted within engineering actually have an increased likelihood in graduation, with an increase of around 20 to 25% between those who shifted and those who didn't. This is actually expected since, as we said before, enrolling in their preferred degree program increased graduation rates by very much. Next, for those who underwent leaves of absence or absences without leaves, we see that students who did not take LOA or AWOL have an increased graduation chance or graduation rate. Then for those who lived in residence halls, we see that living in residence halls doesn't actually have a significant effect on graduation rate. And for those who had scholarships, we see that students who have scholarships are more likely to graduate than those who didn't. Next, looking at the continuous factors, we first have age of entry to UP Diliman. So we see in the college and EEI level that older students have a slightly lower chances of graduation in the EEI, while in the college, age doesn't have an effect at all. For high school GWA, we see that higher high school GWA leads to higher graduation chances for students. And for UPCAT Science T-score, we see that there's a positive trend between higher Science T-scores and graduation chances. Next, for UPCAT Math score, it's the same as the Science T-score. There's a positive trend. This is the factor with the highest positive trend among all the continuous factors. Yes. And next, for UPCAT Reading Comprehension T-score, we see that while graduation is not strongly correlated to reading comprehension, there is a slight negative slope to this plot. So it means that students with higher reading comprehension T-scores have a slightly lower chance of graduation in the college and EEI. And finally, for UPCAT Language Proficiency T-score, we see that language also has a minimal negative effect on graduation. So that's it for the statistical analysis of our data. Next, after discussing the relationship of each factor with the output, we will now be discussing how these factors together affect the graduation status. To do so, we first present the results of the logistic regression model. From this table, we see that for all data sets, the p-values are less than 0.05, which means that at the 0.05 level, all models are significant. Additionally, we can also see that for model 1, the R-squared values range between 0.1 and 0.24, which means that while some of the datasets, such as the EC and EE datasets, are already good fit models, the rest of the datasets in model 1 are not good fit models yet. In comparison, we see that for model 2, the range of the pseudo R-squared values go from 0.33 to 0.6, meaning that all datasets are considered as good fit models already for model 2. Moreover, there is around a 0.2 increase between the R-squared values of the model 1 and model 2, which we can use to conclude that post-matriculation factors are important in modeling graduation status. Now, in order to compress the discussion on factor analysis, we have decided to present only the analysis results for model 2, since it has a far higher pseudo R-squared value compared to model 1. This table presents the results of the Wild chi-squared test, where only cells where the p-value was found to be significant was retained. From this, we can see that for the continuous and bicategorical factors, the following were not found to be significant. UPCAT Science T-score, UPCAT Language T-score, ethnic group member, dependent on UP faculty or employee. So these were removed from the tables entirely. Next, looking further at each of these significant factors, we look at the odds ratio from each of these. This table presents those results as well as the 95% confidence interval. From this table, we can see that age increase has a negative effect on graduation, at least for the EEE, ECE, and CS datasets. On the other hand, enrolling in their preferred degree program, having a higher math T-score, UPCAT math T-score, and higher high school GWA have positive effects on most of the datasets. Next, for post-matriculation factors, we first look at this table for the World Chi-squared results. We see from this that 3 out of the 4 post-matriculation factors are significant in most datasets. If we're going to look at the odds ratio, we see from here that not going into AWOL or LOA and having scholarship helps increase graduation chances, while students who shift within engineering have a much higher chances of graduation as compared to those who didn't. Next, looking at the multi-categorical factors, we make the following observations. All multi-categorical factors are significant to at least one dataset. The COE and the EE datasets have no multi-categorical factors that were significant. Religion has no significant categories in any dataset, even though religion was found to be significant in the all and non-CS datasets. And finally, high school province only has significant categories in the all dataset, even though it's also significant in the non-CS, EEE, and ECE datasets. It should be noted that those marked with asterisks here are factors that were found to be significant in that particular dataset, but didn't have any significant categories in that dataset. Further looking at each of these multi-categorical factors, we first look at year of first enrollment. We see from this table that for the all ECE and CS datasets, 2009 students are at least 10 times more likely to graduate than 2011 onwards students. Next, for the entry degree program of students, we see that for the all dataset and the non-CS dataset, the BSCS, BS Check, BS COE, BS ECE, and BSEE have a significant negative effect on graduation. And for the EEE dataset, BS COE has 0.5 time BS COE has half the chance of graduation of BSEE students. Then next, for address location, we see from this table that since the numbers are much greater than 1, living near the university campus has a very positive effect on graduation. And next, for high school province, those who studied in NCR are 2.5 times more likely to graduate than those who studied abroad. And finally, for STFAP bracket, we see that bracket A and B students are more likely to graduate than bracket D and E1 students in the EEE and the ECE level or datasets. Finally, the results of the predictive models are as presented here. First, looking at this table, we see that the neural network model has the highest precision scores and lowest false positive rates, while the SVM or support vector machine has the highest recall rates. Generally, the machine learning models performed better than the logistic regression model in these 3 metrics. Next, that was for model 1, the previous one. This one is for model 2, which includes the post-matriculation factors. We see from here that the logistic regression model has the best recall, while for all 3 models, we find that the precision scores are pretty similar, with variances of around 1 to 2% only between the 3 models. On the other hand, for the false positive rate, we see that it varies largely between the models for each data set. so we can't make any concrete conclusions about which of these yield the lowest false positive rate. So in addition to that, we also have the accuracy and F measure metrics. So from these tables, we see that the results of all three models are doesn't vary by much, with less than 5% difference between the models for accuracy and F measure in both Model 1 and Model 2. It should also be noted that if we look at Model 2, there's a large increase in accuracy in F measures as compared to the Model 1 scores. Therefore, our previous conclusion that post-matriculation factors are important still holds here. Next, looking at the receiver operating characteristic curve, we see we present here the ROC curve for the all data set for Model 1 and Model 2. So we see here that for the training data set, the SVM has the highest training score for Model 1, while neural networks has the highest training score for Model 2, while for the test data sets, all three models yield pretty much the same ROC curves. We will not be presenting the ROC curves for the other data sets, as the other data, the curves for this look pretty similar to this one already. And finally, looking at the AUC scores, which we got from the ROC curve, we can see that the AUC scores increased significantly between Model 1 and Model 2. And for Model 1, SVM and neural network have better class separability, while for Model 2, logistic regression and neural network have better separability. Now, to wrap up our discussion, first we present the relevant results from factor analysis, which are as follows. First, enrolling in preferred degree program increases graduation odds by as much as 14 times. Students with permanent addresses near the campus are at least 13.6 times more likely to graduate. Students from high schools in NCR are 2.4 times more likely to graduate. Higher UPCAT math scores and higher high school GWA result in higher graduation odds. Older freshmen are less likely to graduate, and students enrolled in EEI, DCHEC, and DCS are less likely to graduate compared to BS-EM students. And students from higher income brackets are 4 to 8 times more likely to graduate. For post-matriculation factors, students who shift within the college are 5 times more likely to graduate than those who didn't. Students who have scholarships are twice as likely to graduate, and students who undergo LOA or AWOL are less likely to graduate. Furthermore, important results from creating the predictive models are as follows. First, including post-matriculation factors is important to make good fit models. For classification, using neural networks yields the best results. For models with high accuracy, all three models yield equally good results. For maximizing class separability, either logistic regression or neural network yield better results than support vector machines. And overall, using neural networks is the best option due to it consistently having good classification scores, high accuracy, and good class separability, making it the most robust model for predicting student graduation probability. Finally, some recommendations for future work. First, for the descriptive analysis part, it is recommended that analysis of students who exited from the college outside of graduation, for example, those who dropped out, shifted out, and transferred, be included in the analysis. Next, studying semesters from first entry to exit and dropout or exit rates for the college and EEI might be beneficial as well. Studying year-on-year persistence in addition to persistence until graduation is also recommended, and studying effects of qualitative factors and other post-matriculation factors such as semestral GWA or student organization affiliation effect on student graduation is also recommended. For factor analysis, we recommend the use of additional tests such as ANOVA to gain more insight on the relationship between the input factors and graduation status. Finally, for predictive models, further improvement can be done on parameter selection for SVM and neural networks using more powerful machines. Next, including higher order interactions in our predictive models might also increase our accuracy or performance metrics. Optimizing the models using accuracy instead of AUC scores might lead to different results in our analysis. And creating new models that can predict on-time graduation, semesters to graduation, and other outputs relevant to the college and the EEI may be beneficial as well. Finally, it is recommended that the study be repeated on students who underwent the K-12 program, since there was a large shift in paradigm, what with our curriculum changing from 5 years to 4 years, which may result in a vastly different analysis and with a different set of pre-matriculation and post-matriculation factors. Thank you. That's the end of my presentation.